Okay, we are going to start by talking about the basics for cognition and looking into what is cognition to explore all the different pieces in cognition, like language, memory, perception. So, we're Memory and Cognition. This is Psych 422. And we're going to start with Chapter 1, just the history section for this module. So Chapter 1 also includes the brain, but you can leave that out. That's the next module. To start, I always like to ask people, what percent of your brain do you think you use? And inevitably, somebody comes up with this 10% rule. And when we get to the brain section, I'll talk about where I think that came from, but really, it's way more than 10%. It's almost the whole brain at once. So, if I ask you to stick your fingers in your ears, close your eyes, and don't think about anything, which is pretty much impossible, you're still using most of your brain. So the brain controls a lot of what we do, and so when people say you only use 10%, they're really talking about this sort of myth on brain usage that isn't really accurate, which we'll get to in the next module. So why are we here? What's the point of this class? Well, we're going to study cognitive psychology, which is the study of the thinking mind. So cognition literally means thinking. In psychology, we're going to study how the individual thinks. So we're going to talk about the mind-brain connection, how the brain actually works, and then on to the pieces of things that you do daily. Attention, memory, language, and why you forget things, and sometimes that's good for you. So why should we study cognition other than I think it's really cool? Well, generally, there's sort of this curiosity on how the brain works and how that makes us the people that we are. So scientists are kind of cats. We're really curious. We want to understand how things work. We want to look into, why do the things happen that happen? We like to show off. So in general, this is working with other researchers. So there's neurocognition. And so you can look at what it is, the little pieces and parts of your brain that cause the things that you do. So like the amygdala controls emotion. I personally work with a lot of clinical psychologists to look at how their scales are worded changes the way people interpret them. So just one little word change somewhere can change all of the output on a traditional depression scale. So we like to collaborate a lot, or get paid a lot. Not me, unfortunately, but applications of cognition are pervasive through your daily life. So if you have a smartphone, you are the benefit of artificial intelligence research. If you are watching TV, that's plenty of advertising research from the behaviorism trend in the 1960s and 70s. If you are driving down the road and you notice stop at a stop sign, that's still the application of cognitive research in your daily life. And these are just sort of my general ideas on why I think cognition is so great. But also have, why am I here? What do I want you to learn the entire semester about cognition? Okay. 3 big things. Psychology is a science. I know you've heard this 1,000 times, but especially cognitive field. So as you'll see here in a minute, history shows that cognition was sort of misaligned as this fancy black box that we couldn't figure out what was going on. And really, it can be a science, and we are a science, even though we're a social science. It still makes us do scientific research. So there will be several discussion boards on how do we make this a science. Okay? And then the 2 general cognitive rules about your brain. We don't like to think very hard. That will come up a lot. When we talk about change blindness or certain perceptual processes, your brain goes, easiest solution, here, done. And we also like new shiny things. So your brain is often attracted to things that are new in your environment, such as a loud noise or if you hear your name somewhere. So those 2 rules sort of apply to a lot of the different cognitive topics we're going to talk about. So keep those in mind. Science, don't think very hard, except when you're studying, and we like new shiny things. Okay? So let's get into the history of cognition. And this is really where our chapter 1 comes in. Ooh, sounds. So we're going to look at how cognition develops, because I think it's pretty important to look into why did we get to the place that we are now as a way to think about how we should move forward in the future. Okay. So, in the beginning, psychology, the whole science really started as a philosophy. So Descartes, Locke, the whole idea of tabula rasa, where we are blank slates versus we're born with these sort of innate rules. And so it really started as a thinking sort of science. So how can we explain the things we see in everyday life? So more philosophy. But the official father of cognitive science is Wundt. Okay. So he had really the first lab in Germany. And so much of the research that we base our stuff on now actually is from Europe, and then the Americas sort of took over after James became so popular. But he was famous for really doing a lot of association sort of tasks. So he gave you the first word and you name the first thing you can think of. So say lost, most people say found first. But really this is a big issue in introspection. So introspection is where you sort of look inside the black box of your brain and say what you're thinking. So when someone asks you, what are you thinking? They're asking you to introspect. There's a lot of problems with this process, but we'll come back to that. So the second one is really Titchener. He was a study of Wundt's who looked at all of mental activity, but he really expanded this in the sensation area. So they would put people in these rooms with these lights on at the end of a hallway, so to speak, and to figure out how much light we had to have for you to perceive that the light was there. I know that sounds like an awful experiment, but it was super important in understanding how your eyes worked. So really, Wundt and Titchener sort of started this idea of how can we study things that we can't see, which is super important, because you can't see people thinking. So, two major contributions from the sort of German folks. Mental activity, so this complicated process of all these thinking, like how do I get to the point where I decide even what's for lunch? That's so complicated. They show that that can be broken down into all these little component pieces, which has gotten even more popular now in the neurology field. Okay. And then they developed some objective methods for assessing mental activity, like the light experiment I described. Okay. The real problem that they had was that it relied too heavily on introspection. So this idea that people, if you ask people what they're thinking, they have some sort of way of actually telling you what they're thinking. They don't lie, which we all know is a problem, social desirability bias. And then they have a good output method. So if you look at asking people simple questions, can you describe what a cat looks like? Most people talk about, well, I imagine what cats look like and then I describe it. But some people would say, well, that's not really the way I did it. So introspection has the problem of the fact that it's not consistent across people, which makes it very subjective. All right, next. So in the Americas, we've got James, very popular. He's written some really great, huge novels on psychology. But he was really focused on a slightly different question. So Titchener's and Wundt's lab was focused on how do we figure out how to get to study the things that we can't see and what is their specific nature. Whereas James focused more on functional. What's the function of a specific mental activity? So the Wundt lab is more descriptive. What are these activities that are going on? This is more functionalist. So where we're trying to figure out these tasks that we have, not tasks, sorry, these things that we do, what is their function in our daily lives? Which is slightly different than this more structuralist approach that says, here are the structures of the brain, now what do they do? So that's more descriptive. Functionalism, more evolutionary. Why do we have the things that we have? So it's really based on a lot of Darwin's ideas. Not quite so much natural selection, but the idea that things evolve that are useful for us, so what is their use? However, we had a problem. Behaviorism came along. So there was a lot of pushback. You can't see these mental activities, so how do we even measure them? So that's where the black box thing came from, Skinner and Watson. And so how do I describe the or even measure these things that people are thinking? So this is a pushback against introspection. Introspection is way too subjective. We can't measure it. It's not countable. So behaviorism really was all about things that we can count and we can see. So Hall's one of the first big guys in this area. And his idea was that internal events of thinking, although they wouldn't have used the word thinking didn't occur for behaviorists, we can figure out what's going on inside from the outside behavior, such as like motivation. So why do people eat? Well, because they're hungry. It's a natural response. Why do people overeat? Well, there's certain motivations and desires for that sort of thing. Skinner is probably the most famous that people recognize his name other than Watson. And we jokingly, I'm teaching a graduate class of memory, and the joke is that it's get off my lawn Skinner, because he's very much against, or was very much against, the idea of an internal event. So he didn't think that we could accurately describe thinking, which is sort of amusing if you think about it, right? Because his thoughts were that we had no thoughts, and we couldn't discuss those sort of actions in our head because we couldn't count them, couldn't see them. So what happened with behaviorism? Because it's not quite as popular. Now we sort of moved to the ABA, the applied behaviorist perspective, where we can change people, like smoking. We can get rid of that using behaviorism principles. A lot of special ed people use behaviorism principles, but why isn't it so popular now? And Chomsky is really the reason for that. So Noam Chomsky, still around doing research on language, and he said that the most interesting thing about people was their language, and you couldn't use behaviorism to describe language. For example, you couldn't use a behaviorist principle on why children say mouses instead of mice. So there's no reason that they could say that. They have never heard the word mouses. Most people say mice, so where did they come up with that? So there's sort of these internal rules that plurals are word plus s. So having those sort of moments, we couldn't explain by not thinking about thinking. It also failed to include things on the nature of perception. So we can't really describe perceptual processes like your eyeballs, which is several modules away, without having that sort of using the internal events kind of rules. So behaviorism sort of hit a wall. They couldn't go any further. So there was a revolt. Mostly started in the late 50s, really took hold in the 70s. Behaviorism started to die out, and cognition has sort of taken over, and now we're sort of blending the two. We're friends now. And cognition, the field, is sort of reaction to behaviorism. So there was a 1957 MIT symposium on cognitive science and the computer. So they presented one of their big new computers, and by big I mean entire buildings worth sort of big, and we're talking about how can we use this framework to describe cognitive science, and it was super effective. So cognition is sort of this sort of pushback against behaviorism, which was, remember, a pushback against introspection. The military actually is one of the largest buyers of sort of applied cognitive research. They really wanted some sort of test to look at what their recruits would be good at doing. So there's lots of IQ testing was built, because in the military they have tests like the ASVAB, and other sort of uses of their cognitive work. So the drones, how those displays are laid out for pilots, lots of different things that the military has picked up as a way to improve their reach, so to speak. So the military really bought a lot of cognitive research because it was helpful for them. And then the super famous paper, which we're going to look at, is Miller's magic number. When Miller was writing this in the 50s, he was collecting a bunch of research on memory. So the magic number 7 plus or minus 2 pieces of information that we can remember. And when he was writing this paper, it was really like, here's a meta-analysis, which is just a collection of a bunch of papers at once, on memory. And everybody's ignoring it because everybody's pushing this behaviorism perspective, and I don't really get that. And it became sort of the turning point, the tide switching towards cognition. He's written several papers after that sort of, he said, I didn't have any idea that when I wrote this paper, this silly little paper, that it would be such a huge like marker for when cognition really started. Alright, so directly tied to the computer. What is it about the computer that helps us understand cognition? What it really did, instead of being like, oh, computers can model things, and these computers couldn't, or computers can be artificially intelligent, which is sort of true, it was really more, here's a way to think about the brain with terms that we can understand. So we talk about the computer has software, so our brain has specific processes that it will run to help us understand color or motion, or the language that you are hearing right now. And then it has hardware, so there are specific parts of the brain, like the frontal lobe and the occipital lobe. And then there are all these processes. So it was a way to use terminology to understand what was going on in the background. And so we used that, it's called the information processing approach, to describe cognition. So it wasn't even necessarily that the computer was there to help us do specific things, it was more of a good, like, mnemonic for us to understand what was going on. So some of the big guys in this field, Simon and Newell, who are really famous artificial intelligence researchers. I think it's Simon that's actually won the Nobel Prize in, I think, economics, but for a lot of his decision-making research that started as artificial intelligence. And then Noam Chomsky, who really was pushing against, he and Skinner kind of got in a lot of little fights about how behaviorism couldn't explain language and why language was so important because it's so pervasive in your daily life. And so we can use this computing machine to understand our cognitive processes. So here's a picture of the binary automatic computer, 1949. So this computer is the size of a building and was used to calculate different telephone routes. So how do we, switchboards kind of an idea, but it's just kind of a neat picture of an older looking computer as I'm recording this from my 13-inch laptop today, right? So a little bit on artificial intelligence. So one of the experiments that you'll do is testing artificial intelligence. It's called the Turing test. And they're actually about to create a movie about Alan Turing and his life and his work on the Enigma project. But really, he was the one who said, here's how we can test for artificial intelligence. Okay, so I have the link for Newell and Simon's work on artificial intelligence, which I'll post online. So really we're taking computers and simulating the mind. So here is a model of how we think things work. Now, does that actually perform like a human does? So the point of artificial intelligence really isn't to build a computer that could be a person in the cognitive field. It's more, here's a model. Now, does it act like people do? So let me give you this picture. So I have some sort of artificial intelligence research. So can I make a computer do something? So language model, perception model, decision making, lots of gambling research is done as artificial intelligence. Can the computer do it? Okay. And then generally something happens here. So there's some sort of wonkiness, it's a non-technical term. The computer does something weird that we didn't expect given what people do. And then we can test that idea. Okay, so here are the parameters. Do people do that if we give the same setting as the computer? Now, we're going to get that data. If people match that, that's something new that we've learned based on computer models. If they don't match that, time to start over and fix our computer model, see what happens. And so it is a cycle in trying to create these pictures of what the brain does. So Siri is a really famous artificial intelligence computer model, but she has some weird moments, right? So you can ask her lots of very strange questions and get some really fun answers out of her. And then sometimes if you've ever used text to speech, so you're trying to not drive in text, but send a message where it is, you speak into it and it types it out for you, if you've ever seen some of those interesting results. Or another famous one is Watson. So IBM put together a computer program that played Jeopardy and beat everybody, of course. So there are uses for this that aren't the sort of what you see in the movies. It's not, I'm trying to build a computer that's going to blow us all up. It's more, I'm trying to build a system that I think models the mind, and here's the things that I've figured out based on that. Okay, so we'll talk about some more of these models as we go. All right, so theories. This section really is about given all of that history, how do we frame cognition in a way that sort of like breaks it down into those component pieces. Okay, so there's several big theories. Mostly we're going to talk about mind and brain. So the mind-brain debate on whether the person, the mind, okay, I'm not using the word soul here, but the idea of the person yourself, is that all from the brain? Is the brain just there to run the processes? So how are those things either one thing or separate? And which brings us to mental representations, which is sort of like how we picture things. Mental processing being like the software, what's going on. And so why do we have to study the brain? So a little bit on each one of these. So the mind-brain connection. We've been talking about computers. So is the mind the software and the brain the hardware? Or are they the same thing and the mind and the brain are both hardware and software? So this is still argued about now, not quite as much. I think we've sort of given up arguing on this. But are they really separate things? So lots of people like to think that the person is somehow separated from the brain. So if you, I don't know, maybe 10 years ago now, the Terry Schiavo case where she was mentally, like her brain had stopped working, but they were keeping her alive on a ventilator. So if there is no brain functioning, is the person still there? This comes up a lot in those kinds of moments where we don't really we have a vegetative state, but you're being kept alive by technology, but is there any brain functioning? I clearly have a bias. If there's no brain functioning, there's no mind, but I'm going to try to prove that to you. Okay. So there's a couple of ways to think about this. I can look at the physiological level, which is the more neuron, that's the more brain piece. So my neurons are firing, what does that mean? And we're going to do the brain next. We're going to talk about all these little pieces. We can also talk about the eyes and ears, so your sensation, all that would be the brain half. And then we could talk about the more mental processes, the thinking half. And people tend to study one or the other, so I think that's where this whole mind-brain separation came from. But really what's going on is that the mind is emergent from brain processes. So what do I mean by that? I'm talking about the brain has specific things that it does, but the interpretation and the construction of reality is emergent. So that's more the mind part. The brain just fires some neurons, which helps you interpret what's going on. Okay. And so I've talked about this already, but the information processing approach is relating the mind to a computer. So thinking about the storage of information. So we have sort of a RAM system, the manipulation of information. We'll talk a lot about false memories and how people come up with things they've never seen but believe that they're true. And the transformation of information. And that one's a little trickier. So I can store things, I can open them up, I can manipulate them, I can restore them, or I could take information and transform it into another form. So as information comes into my sensation, I have to transform that into something I understand. So if you know anything about your eyes, the information is upside down and left goes to right, right to left. So your brain has to transform that into a picture that you would comprehend. A little more on mental representations because they're super neat. And we're going to do a lot about this, so this is a term that you really need to get down. So representation is a physical state. Okay, and that's a tricky one. So it can be a neural message, it could be an imagery, so like imagine what your cat or dog looks like. It can be a stop sign, So it can be any sort of physical states. It's a very loosely defined term that conveys some sort of information. So the stop sign, the color red, we know means stop. The letters have a specific information piece that you understand. Okay, so that information specifies something to you. Objects, events, categories. When you get birthday cards in the mail, the cake represents something to you. So it's a physical state, it's a picture, and that conveys the information, happy birthday. So there's two distinct parts that we're going to talk about for representation. A format, the way that it conveys the information to you, so picture, neural message, all that stuff, and then the actual content of the message. What does that mean to you? So we're separating how the message looks and what the message means. Alright, so an example. The ball, or a ball, is on a box. So I can think about that in what's called propositional representation. We'll do this more when we get to language, but it's more of like how a computer might interpret it. So ball on box. It's giving you a relationship rule, it's giving you syntax, it's very abstract, so I don't have any sort of picture. Or, so that's this side. On this side, I can do a picture of it, so I can imagine what a ball looks like on a box. Okay, and that's much more concrete. Most people think about all representations in this format, but we'll talk a little bit about these and how this is mostly how language works, and this is more how imagery works. So we're breaking this down. We've gone from mind and brain. Now we're going to talk about what's in the mind's mental representations. Now what happens? So how do we work on that information processing approach? Okay. So it's called mental processing. And the process is the transformation piece of information processing. So there are specific inputs to specific outputs. So when light comes into your eyeballs, there are rods and cones which take that specific input, color, how light or dark it is, and translated that to a specific output that you understand. Okay. Processing system is a group of processes that work together to accomplish something. So I keep talking about perception because it is so neat, because when we look at how complicated perception is, it's sort of amazing that we ever see anything. So just processing this screen and listening to me at the same time is actually a whole bunch of different little processes running at once. So we have an area of our brain that encodes sensory information, we have an area of our brain that encodes the language information, the whole back half of your brain is devoted to vision, where things are in the space and movement. So putting all of that together is a processing system. Okay. And then the algorithm is kind of, to me, a little redundant, but it's this idea that within a process there are step-by-step procedures. First do this, then this, then this, then this. So the way it really works is we have a processing system, which has lots of little processes that work together to help you understand something, and all of those have their own little algorithms. Okay, so system's probably the biggest, then process, then algorithm. Alright, so summing it up now. All of that is fantastic, it's great, but you told me this was science. So how is all of this science? Okay. So how can we test thinking? So asking people to think about their thinking, I've already said, was bad. So what do we do that's thinking? So this is your very, very basic review of experimental design. Okay. And I'm partial because I'm a social scientist and I think experiments are really awesome, very neat. So they have several parts. But the whole point of experiments is to look for a causal relationship. So X causes Y. So you hear all the time that violent video games cause violence. And really, do they? Is it a causal design? Okay, so how can we test causal things? Well, that means you have to manipulate variables. So if I want to test this violence issue, I would have to make some people play the violent video games and some people play the non-violent video games. I've manipulated that. I have control over it. Most people don't do that because it's kind of hard to get people to do one or the other, especially for a long time. So what happens if you can't manipulate things, especially for ethical reasons? So let's say you want to study smoking and cancer, you can't make some people smoke and some people not smoke. If you want to study preterm birth weight, you can't really make babies, preemie babies versus not. Ethics. So those are more correlational studies. And there's a lot in that in the brain section because we can't just hack out parts of people's brains. They don't really like that. So I can't manipulate variables. It's all correlational. So most of that violence video game stuff is correlational. People who play violent video games are correlated with people who are more violent. Again, still a tricky issue. So what are the parts of experiments? So back to my violence in video games. So I have an independent variable that is nonviolent versus violent. Now, if I could manipulate it. So that's usually sort of a grouping variable. Like I have an experimental group or a control group. Our lab studies language. So we look at how people use language, and let's say thinking about your traditional QWERTY keyboard. How does that affect the way you feel about words? So I don't really have an experimental group in that or control group. What I do is I look at how people rate word pleasantness and look at how those words are typed. So my independent variable is more like typing style. How many times does it switch fingers? How much of the keys are on the left hand versus the right hand? So it's still manipulated. I can look at left-handed words, right-handed words, but it doesn't really have an experimental group. So that's not always the case, just usually the case with the experimental control group stuff. Then I have to pick something to measure. So my dependent variable is the thing that I'm actually interested in measuring. So my typing study, I'm measuring how pleasant they think words are based on how they're typed. So the based on part is the IV, what I'm actually measuring, the DV. In our violence study, we would measure some sort of aggression or acts of violence, something along that nature. The problem is that we often have a lot of these noise variables. They have lots of names: extraneous variables, noise variables, confounding variables, third variables, all the same thing. This idea that there's this extra stuff going on that causes some problems in your experimental design. So in our violent video games example, maybe it's the other way around. People who like violence are drawn to violent video games. Or the correlation's kind of small because there are lots of people who play video games that don't do anything. And gender is often an extraneous variable as well. So in my typing study, one of the extraneous variables that we are actually interested in is expertise. How fast do people type? That changes your relationship between typing of the word and how pleasant you think it is quite a lot. Alright, so what's the point of all this stuff? So we've got the science, we've got the history, and then we've got how we study cognition. I really, really want to hit on this. This whole thing is a science. So we're testing this through experiments. Artificial intelligence research, also experimental design. Even though once research was considered sort of weird because of the introspection, he often manipulated things and asked people questions. So the DV, not so much, but the IV is still experimental. So it's all about the science component. And the idea of experiments. So why do experiments? Experiments lead us to these theories. We'll talk about a lot of different theories across this semester, not just the mind-brain connection, which lead to more experiments. So thankfully it keeps me in a job. The idea that I have this experiment, which leads me to this next question, which leads me to this next experiment. So it's a very continuous process. So one of the points of the research project, or the research trace that you're going to do, is to think about this experiment. This paper was inspired by this paper, which was inspired by this paper. So looking at how science is sort of a flow and not just a one-shot experiment. Okay. So why should we care? What's the important part of all of this? And to me, even if I'm doing very basic research, people use that in the field somehow. So business, we're talking about advertising, the military, artificial intelligence research on your computer, functional design of the way things look, all are based on cognitive research and some other stuff, social science, social research, or sociology even. And so thinking about these sort of basic processes really helps us understand all our everyday life. So in each section I'll try to give you an idea of why it's important. So why should you care about these like very basic perceptual things? Well, that's because it's the way illusions work, or the way that we know the advertising, why they use the bright colors, because it captures your attention. So really thinking about how these things apply to the things you do on a normal day. And that should be it for this section.